Okay, welcome back. In the last lecture, we derived the expression of fugacity as a function of molar volume, and this was the derivation which connects to the integration of this term from 0 to p to this fugacity coefficient. Okay, I can continue this exercise. Particularly, we can look at for pure fluid when yi is equal to 1, Vi bar is molar volume. And in that case, this expression is Fi by P for pure of I is 0 to P Vi minus RT by P dP. Okay. I can also rewrite this expression by taking this RT in to the right hand side. And this could be simply Zi minus 1 divided by P dP, where Zi is nothing but compressibility factor. Okay. Now consider one approximation. So consider an approximation. Now before I write that, we should make a note that this expression which we have got for a component I in a mixture connecting to the fugacity to the molar volume for the mixture and for the pure, these are exact expression. Okay, there is no approximation involved in this expression. Now we can make certain approximation to simplify and look at how from here we can come up with this Lewis fugacity rule which we have imposed earlier. Okay. So if I consider this approximation where I said that, well, if the mixture follows Amagat's law, okay, which is nothing but the additivity of the volume concept. Okay, this is I equal to m. So that means you are simply adding up the volume. This means that Vi bar is equal to Vi, okay, for the mixtures. Okay, or when somebody writes this actually means this also, and which essentially also means from here is mix. Okay, this is equivalently also implies that this is equal to 0. Okay, or V excess is also 0. So this is the Amagat's law. Okay. Now if we have this information, that means I can write the partial molar volume of component I as simply molar volume of component I, and I can plug in here now this, right, this, if I using this kind of approximation, then what we get, RT ln phi YIP is equal to 0 to P Vi. Instead of Vi bar, I am writing Vi minus RT by P dP. This expression, looking at this, okay, what is this? This is nothing but RT ln F by P of pure I. That is what by definition. If you look at, this is what by definition, right? This is the definition. So you have this now, left hand side this and right hand is this. Now if you can simplify, what you get is the following expression: F I T P composition is yi times f pure I at Tp. Okay. This is nothing but Lewis fugacity rule. Okay. So, note that this is at the fugacity of the pure component I at the temperature pressure of the mixtures. Okay. Now, I will try to describe this, the validity of such a rule, okay, Lewis fugacity rule, by taking an example from the literature. So, the one which we just derived, okay, was based on the additivity of the volume for all the components. Okay. So, thus it is a very simple equation which inherently depends on the fact that the volume should be additive for the mixtures. Okay. So, it turns out that at high temperature, okay, this is a good approximation, because in liquid like densities fluid tend to mix with little or no change in volume. Okay. So, let us look at the example of nitrogen butane volumetric data at a specific temperature 171 degrees Celsius. Okay. So, this is an example taken from the literature due to Evans and Watson, and the data is 1956 data. So, what we have is the following, that this is compressibility factor, right, as a function of the composition of nitrogen and the butane. The nitrogen is close to 0.9. So, this is basically the compressibility factor as a function of mole fraction of butane. Okay. So, this is the data directly from Evans and Watson work in 1956. So, the question is, can we apply Lewis fugacity rule here? By looking at the data, you may be tempted that, well, since the Lewis fugacity rule states that the fugacity of a component I in a mixture is nothing but the mole fraction multiplied by the fugacity of the pure component at the same temperature and pressure. So, it is like a linear relation. So, looking at here, if you are looking at the high this pressure, okay, at here it is a linear region, okay, as a function of the mole fraction. So, you may be tempted, well, is a straight line function as a mole fraction. At first glance, you might be tempted to conclude that this system at here and 171 degree, the Lewis fugacity rule should give an excellent approximation for fugacity of component. So, it looks very obvious that, well, this should be fine, why I can simply apply that, because if I am interested in the pressure, let us say 690 bar, I should be able to apply. It looks from the derivation that, well, this is not from the derivation, from the final expression, that this is simply f is equal to f yi multiply f of pure. But then if you carefully look at it, okay, the pressure has a significant effect on this z as a function of mole fraction. It is not linear, okay, and this is the region which clearly tells you that low pressure, it is certainly does not behave similarly as in the case of higher pressure. Higher pressure you can see the linearity, but low pressure it is not. Okay. Now, does that affect this data or it does not affect? I mean, can I actually apply this relation at 690 bar, this Lewis fugacity rule? I cannot, because at lower pressure it behaves completely different. In other words, in a linear case you can add the volume, but when it is non-linear, can we simply add the volume in the way which we expect in the assumption for the Lewis fugacity rule? So, the answer is actually the conclusion which we wanted to apply is not justifiable. Okay. And the reason is that when we made use of the Lewis fugacity relation, or rather when we derived the Lewis fugacity relation, the assumption was that this additivity will valid from pressure 0 to the pressure P. It is from 0 to P. That integration is from 0 to P. So, it assumes additivity of volume. The Louis-Fugate rule assumes the additivity of volume not only at the pressure of interest, which we thought here, but also for the entire range from 0 to P. You look at this derivation, we made use of this, right. We, due to the additivity, we replaced V I is equal to V I, but this assumption is not at P, it is for the whole range. So, if you are blindly applying this Fugacity rule at 690 bar, ignoring the fact that it behaves differently, then naturally the results are going to be incorrect. Okay.
0 to P should be linear.
So, 0 to P, the assumption of the volumetric should be linear. Yeah.
Sir, why are you taking linear curve only?
No, this is not a linear curve. This is the data which we got it from the literature. So you have done an experiment and you calculated the compressibility and you plotted against the mole fraction. That is what. So, it shows that when you have linear, Z is a function of linear, which essentially means since here in this line, if you look at in this line, the temperature and the pressure is fixed because temperature is 171. Okay. Now, temperature and pressure is fixed. So, in this along this line, what is happening is Z is increasing as a function of mole fraction. That means, the volume is basically changing linearly as a function of mole fraction, and thus it is linear. That means, it is additive, whereas in the other case it is not. And this is the reason that in here just looking at this higher pressure, you cannot do that. You cannot make use of this approximation, but at lower regime you can. Low regime, what I wanted to say was at higher you may look like at this regime it works fine, but the lower ones, they do not follow the Amagat's law, okay, follow this relation. So, that means this relation do not hold. Okay. So, this is what I was mentioning here, that V I bar in the Fugacity expression is a part of an integral. Thus, assumption one wishes to make about V I should, whatever assumption, if not just assumption of Amagat's law, but whatever assumption you are going to make it for V I bar should hold over the entire range of integration. Okay. So, this is an important part. So, now having gone through the bit of example, what we can now do is talk about Fugacity of a component in a mixture at moderate pressure. Okay. What the idea behind this one is basically that P is not equal to 0 or not even close to 0. Okay. We are considering pressure which is reasonably moderate. So, the best way to explain is to make use of some equation of state. So, what we are going to do is we are going to make use of what Progenies came up with to explain this. So, here we are going to make use of Progenies calculation of Fugacity, okay, of component I in the mixture described by modified van der Waal equation. Okay. So, van der Waal equation, okay, valid, which is valid up to moderate pressure. Now, because van der Waal equation has some limitation, so it is not like valid for all conditions. So, what does van der Waal equation talks about? So, I will write it in a way which is simpler to understand. So, if you look at V, so here P multiplied by molar volume for a pure fluid, let us say, is equal to RT, then it is a ideal gas, correct. It adds up the term B minus A by RT by P. Okay. So, if you rearrange, you get a van der Waal equation. So, what I am going to do is I am going to you can expand this a bit, and then this will become like modified van der Waal equation, okay, and this will be the higher this will be higher terms in P square and P3, okay. So what Prajnesh did was he made use of van der Waal equation, he wrote in this form, and now the question is, given this relation of the pressure volume, as we said the volumetric data are given in terms of equation of state, how do you calculate now the fugacity? So, fugacity, how do you calculate, right? So, we know that for calculation of fugacity we need to find out partial molar volume. So, the question turns out that how do we calculate partial molar volume. So, we write down this expression. So, this is the generic expression, does not talk about anything about I did mention that I have written for pure system, but in this case it could be for mixtures also, okay. So, if it is for mixtures you have to multiply V by NT, that is it. So, we will rearrange, ignore the higher terms, and again we are talking about V as a function of Tp N, okay. And now I will write it here V as NT RT by plus NTB minus NTA by RT. Okay, so you have this expression, right? Now, of course, you know how to calculate the partial molar property. If we talk about only, let us say, a binary mixture, then V1 bar is del V by del N1 Tp N2, and this will be your RT by P plus del NTB by del N1 minus 1 by RT del NTA by del N1. Okay. The reason I did not just directly went and assumed B to be constant, because B is a coefficient of the mixtures equation of state, which depends on the composition of it, okay, which depends on the interaction parameter of it. Okay, so so what is in general, what is A and B here in van der Waal equation? So, B represent the size and A represent the attractive forces, okay, the interaction between the particles. Now, what would be the A and B for mixture? Okay. And it depends on composition, right. So, what would be the mixing rule? We must specify mixing rule, okay. So, we will directly use what originally van der Waal proposed, okay, which was A is equal to y1 square A1 plus 2 y1 y2 A1 A2 plus y2 square A2, okay, and B was simply the weighted average of those individual sizes. For this is for binary mixture, okay. Now, I can actually make use of this expression and calculate NT-A, because that NT-A here and NT-B is here, NT-A is here. So, I can write NT-A as N1 square A1 plus 2 N1 N2 plus N2 square A divided by NT, and NTB is N1B 1 plus N2B2. Now, you can take the partial derivative because you have this information of this term. So, when you take the partial derivatives, V1 is equal to del V by del L1 Tp N2. Okay, this is nothing but RT by P, okay, RT by P, and then when you take the derivative with respect to N1, NTB is here, so that is going to be only B1, right. So, second term is nothing but B1, and the B1, and then you have NT also, which is which is, yeah, of course that is fine. Then you have minus RT, and then you have this term which you have to worry about. So, you have minus RT. I am going to write down the expression, how we got whatever the expression we got. Plus A1 A2, and within here we have minus NT square A. Okay. So, this is okay. So, this is part of this numerator minus NT square A. Okay. Now, you have this expression, you can now plug in this expression in the right hand side of the expression corresponding to the fugacity. Remember that. Okay. So, when you plug in this equation, what you got? Okay, you have phi 1, which is f1 by y1p. This is fugacity coefficient for component 1. This is nothing but exponential b1 minus a1 by RT p by RT. Okay, that is one part, because you have this part. Okay, this is one part. Okay. So, if you plug in here, you got what, RT by P, which got cancelled, right, and then you can rearrange this expression. So, if you so what this is V1 minus RT by P. So, if you take this here, you got actually B1 minus 1 by RT. Okay. So, this is actually not the case. So, you got a simplified expression here. This is another term will come up here, exponential multiplied by A1 minus A2 square Y2 square P RT square. Okay. So, this is the term which you are going to get. Okay. This becomes simplified. Now, these two terms, if you look at very carefully, so this phi, which is your fugacity coefficient, contains two terms based on van der Waals equation of state. The second term is dependent on A2, okay, but the first term is independent of A2. Okay. So, if I consider y2 goes to 0, which essentially means pure 1, okay, then f1 pure 1 is going to be simply p multiplied by exponential b1 minus a1 by RT multiplied by p by RT, right. That is what it is saying, right. Okay. So, which essentially tells you that this term or if you take this this term is nothing but your f pure 1 divided by p. This is what it is saying. So, what you have this expression finally f1 by y1 p f pure 1 by p and the second term, right. So, you have f1 as y1 f pure 1, and then you have this exponential term okay. So, this is the problem. Now, if you look at this expression, then remember that this is nothing but the fugacity rules is talking about. This is the additional correction. This is nothing but correction to Lewis fugacity rule. Okay. right. So, this expression you take a note, and then I will just take in one example. This, as I said here, this is only when you have the condition where you are saying that this correction is added when you have situations which are that y 2 is not equal to 0, right, and a 1 is not equal to a 2. So, if a 1 is equal to a 2, which essentially means similar component, okay, and if I 2 equal to 0 means basically nothing but pure 1. So, you have a condition where you have to include a term like that, and this is the reason that Lewis-Fugacity rule may not work in many cases. So, typically Lewis-Fugacity rule for a component I is often poor or is a bad approximation when y of that component is much less than 1. Okay. Lewis-Fugacity rule is usually good when y I is close to unity. So, for example, if y 1 is close to 1, then of course means that y 2 is close to 0. In that case, this particular expression will hold. So, this is what is talking about. Y 1 is much less than 1, then considering f 1 is y 1 f pure is a bad approximation. Okay. When y 1 is much less than 1, then Lewis-Fugacity rule would be a bad approximation. That is what it is talking about. You can say that because when y 1 is much less than 1, it means y 2 is going to be not 0, significantly more than 0, and thus this correction has to be included. So, let us take an example here. This is an example of fugacity coefficient of hydrocarbons in a binary mixture with N2 nitrogen. Okay. So, what we have is fugacity coefficient of hydrocarbon as a function of total pressure for different hydrocarbons. Okay. So, here nitrogen is 2, okay, and hydrocarbon is 1. Okay. So, for each of this we have considered mole fraction of 0.1 for hydrocarbon, okay, and the temperature is fixed. Okay. So, this is a fugacity of y 1 or fugacity of component 1, sorry, okay, f 1 here. So, this is nothing but f 1. Okay. Now, in this case y 1 is much less than 1, right, is not it, 0.1, it is not 1, it is very lower than 1. So, but you look at this is the actual fugacity coefficient as a function of total pressure, but this is the one which is from the Lewis rule, and thus it is very clear that in this condition, since y 1 is much less than 0.1 and y 2 square is closer to 1, because y 2 square is part of this one, or y 2 is closer to 1. Okay. And thus this rule cannot be applied, and this deviates from the actual value. But there is another important thing is that in addition to the composition, the sizes of this system hydrocarbon and nitrogen is quite different, okay, and the intermolecular forces are also different. So, difference in the intermolecular forces between butane and nitrogen is large, given that that means this value is going to be non-zero. Okay. That means this, in addition to this term, this is also playing a role in this case, because these are dissimilar molecules, and thus it deviates from this. Okay. So, these are the considerations which you have to apply before making use of these kind of expressions, because the expressions such as Lewis-Fugacity rule are based on assumptions. Okay. So, one need to take a judicious consideration of such a expression for any applications. Okay. So, this was the kind of example which we wanted to cover as far as this lecture is concerned. We will end here. We will see you next time.